So we looked at the equilibrium criteria for a constant NVU system, which would be like some sort of adiabatic batch reactor. But more commonly, or like in real life, a reactor would not be run under those conditions, but rather, more commonly, reactions are run under constant N pressure and temperature conditions. So constant NPT conditions. Okay? And so for this type of reactor, what we can imagine is our very trusty piston cylinder setup. Where we have some constant pressure. Okay? The whole system sits in a constant temperature reservoir. Our reaction mixture is inside. And there could be like heat transfer going in or heat transfer going out of the system in order to keep it at that constant temperature. All right, and so for constant NPT systems, if you recall, for those systems to reach equilibrium, what had to happen is that their Gibbs energy is not maximized, but it's minimized. Okay. All right, and so we saw previously for mixtures back in chapter 8 that the fundamental equation for Gibbs energy was VdP minus SdT plus the summation of mu I dni. And so here, we're dealing with a constant pressure and a constant temperature system, so those terms go away. Right? And so what we're left with is the mu I dni, and what we could do here is we could replace the dni again with nu I d epsilon. Okay, so we get dg is equal to mu I nu I d epsilon. All right, and so for this system to reach equilibrium, delta G, or the Gibbs energy, needs to be minimized. And so to plot what this means again, in the fundamental equation, we're shown that epsilon is that canonical variable left over. And so if we were plotting this, we would say that our Gibbs energy, if we said it was a function of epsilon, for the system to be at equilibrium, that Gibbs energy would have to be minimum at some value of epsilon. Okay? And so mathematically that's expressed as dg d epsilon at constant npt, which we know from our fundamental equation is nu I mu I. That this sum has to be equal to 0 as well. Okay? All right, and so if you notice here, that the sum of nu I mu I being equal to 0, that's the same thing we got, the same equilibrium criteria we got for the NVU system. All right? So in both cases, and almost in general, the sum of nu I mu I being equal to 0, that would tell you that your system is at equilibrium. The last thing I want to mention, at least when it comes to defining the equilibrium criteria, is that so far we were just kind of generally looking at one type of reaction implicitly. But if you're dealing with systems where you had multiple linearly independent reactions. Then, what your equilibrium criteria would be, it would still be the same thing, mathematically, except your stoichiometric coefficients would now belong to a particular reaction. And this would have to be true for each of the reactions in your system.